I'm Jerzy Pryga, and I'm a PhD student at the University of the National Education Commission under supervision of Professor Krzysztof Woźniak and Dr. Łukasz Wiebrzycki. And I would like to share what I do as part of my PhD project, which, well, is now titled Cosmic Watch-based Detector Array. So I will try to start with some motivation. Then I will briefly explain my detector and share some results of measurements. And then I will talk a little about simulations of scintillator detectors. So let's start. We all know what CREDO is, obviously, but to me, there are three major goals and some foundations of what are our goals, which is global cosmic ray studies, search for cosmic ray ensembles, and popularization and education science. So we want to search for some correlations, anomalies in secondary cosmic ray flags, and it doesn't matter what cosmic rays exactly. We are searching for correlations between extensive air showers, and we want to use citizen science for those purposes. So to meet those goals, we need some detectors, obviously. And let's start by thinking about some dream device that would be perfect for our goals. There's quite a long wish list here. Such device should have relatively big surface, so it can catch a lot of particles. It should be able to identify extensive air showers, had good parameters like temporal resolution, low background. If it could distinguish between different types of particles, it would be great. And it should also be relatively inexpensive, small, so we don't have to search for a lot of space to build it and place it. And it should be able to operate and collect data for a very long period of time so we can study long-term phenomena. So we have smartphones, but they are cool, they are cheap, they are almost free, but they are not sufficient for all those tasks that we would like to perform. So we thought about creating a detector array because it's a simple system which you can, well, expand. You can use any type of detector actually, which you like. And we decided to use Cosmic Watch, which is small scintillator detector. And it is already tested. We know it works, so we don't have to do everything from scratch. And it's relatively cheap, and it's quite a good performance. And detector arrays also have this good property that they can hypothetically distinguish single particles from extensive air shower events. So this is how original design of Cosmic Watch looks like, and this is how mine prototype well currently looks like. It's a little uglier, but it does the same thing. So now let's consider our real detector and how it works comparing to our perfect ideal detector. So the surface is well, I will say medium because it's much larger than smartphones, but it's still 5 by 5 centimeters for each scintillator, but it can detect around 1 to 2 particles per second if we consider the whole array. So I think it's not bad. We can identify extensive air shower events by having flat coincidences. Temporal resolution is much better than for smartphones. Well, currently it's around dozens of microseconds. Maybe it can be better, but it requires some software optimization. Unfortunately, scintillators cannot distinguish between different types of particles. So we have to keep that point. Level of background is relatively low. We can even make it lower by making the threshold for signal to be higher, but it's, well, to choose optimal threshold, we need more tests and more calculations. It's easy to construct. I bet that if I could do that, any high school student could do this as well if we provide him or her with good preparations and instructions and materials. It's small because it can fit on your table, and it's inexpensive in a way that even some individuals can afford a small array. I will talk about cost later, and it's obviously can operate for a long period of time without any interruption. So that's great. So how our detector array actually works, here is a little scheme. We have some detectors, we have a coincidence circuit, and detectors are connected to it. Everything is operated by some microcontroller, which saves data to a card. It can save data directly to the database via internet, and you can synchronize its time also with the time served. So you just need an Ethernet wire and a power supply. You plug it to the master, which contains coincidence circuit and microcontroller. You connect detectors to it, and you have an array ready to operate. This is how it looks like currently. I know it looks ugly, but it works, trust me. So currently for this Cosmic Watch based detectors, here we have the master unit with coincidence circuit and all other stuff. This is how it looked in a box that I used to make outdoors measurements. And about signal processing and how the coincidence actually works. So basically, we have a signal from two detectors, which looks like that, where they are just signals from silicon photomultipliers that are amplified by some factor. Then they meet a monostable circuit which produces a rectangular signal of given length. Then all of the inputs go to the OR gates, which produce a signal, another one that of the same length. Then we have another circuit that produces a trigger signal for our microcontroller and a window signal for our parallel register. And from the first monostable circuits, all signals go to this parallel register, which then turns them into like a digital word that we can read with our microcontroller, and then we can see if there was two signals at the same time, for example, from detector number 1 and number 4. And about the length of this coincidence time, so we consider a coincidence when there are two particles hit different detectors, and the time between them is smaller than some value we choose. This value we choose as this coincidence length is T0, and we have to set this delta T, which is the delay on some of these circuits, plus time of this window from the second monostable circuit. And in order to signal to be registered by the parallel register, it has to be longer than this window. So at the end of the window, the state of the signal has to be set to high, and then we record the signal. So we can actually modify these times in some range and change and choose the optimal time, and maybe see if there are any difference in measurements and results if we set it to different value. Okay, about the data collection. Currently, we only record data on our SD card, but and it's very slow. But it's a problem of software optimization mostly, and also probably sending data to the server would be faster. So in the future, we would like to develop this feature. So we would have much faster data acquisition, that data that could be directly stay on server, and we could use both Wi-Fi and both Ethernet connections with our microcontroller. Those are the possibilities. Well, about data format, I believe it will be a discussion later today. But currently, it's just a table of some values. But we can have access to time of each detection. We have temperature at the time, pressure at the time measured by sensor inside the master unit. And we know from what input there was a signal. So I think it's like a good information not to know just what was the signal, if there was a signal, but from which device it was, because you can detect some, for example, errors. When one device sudden drop of signals by half, you probably can see that, well, something is malfunctioning. Maybe I need to go there and check this out. Maybe it's damaged or something. And you can see an example of a coincidence event here when you had a signal at detector number 2 and number 4. Okay, what about the price? Well, the most important factor probably, and the biggest advantage of this design is that it's probably the cheapest of those larger detectors we will see today, because one cosmic watch should cost around 125 US dollars. It can depend mostly on the price of scintillator, because, well, it's sometimes those prices fluctuate a lot. The master unit, well, the highest price is we have to pay for the microcontroller. Other parts are relatively cheap. And you need obviously some other equipment to put it in some box and have to, so we can have some outdoors measurements, but I don't think they're out of costs. So our target is to create an array of 8 detectors, because with current design, 8 is like the maximum we can get in the actual electronics without any additional changes. So it would cost probably around $1,200 plus the assembly costs, which, well, if it's one detector, then I can build it myself. So costs are only my time and effort. But if you would like to build a lot of them, then there would be some real assembly costs. But it's hard to estimate now. Okay, so let's talk about measurements now. Here is a photo of a place where the first measurements were conducted. So it was basically in the lab at my faculty where I was building this. It's on the ground floor in a 5-story building, so there's a lot of floors and walls that can stop the radiation and cosmic rays, and maybe produce even secondary particles. So it was in the best place. The second one was at my home, which you can see it's near the some window and some balcony. So there was more windows and some less, shielding, I could say. Third measurement, I don't have photo here. It was at the balcony, this balcony right here. So it was basically like 3 meters that way from this site. And the last measurement was conducted at the greenhouse at the rooftop of our faculty. So I thought this like the best place probably, because you can have only a thin layer of glass and an open sky above it. But it was all short measurements because I finished modifying and design like very recently. So now we can go to results of the measurements. Here we have number of key-fold coincidences per hour, and different colors represent different measurements. So you can see that there are quite big differences between different conditions. What surprised me the most is that frequency of signals at the greenhouse measurements was lower than those at my balcony. And it was even a little lower than frequency of signals when I measured it in my bedroom. So something's happening here, but it was, as you can see, very short measurements. One day, well, the longest was outdoors measurements at the balcony, which lasted 69 hours. I have a table here for numbers, but you can see that the differences are significant. At the balcony, you had like 1.7 times number of events more than in the lab. I mean, single events, single detections, and about double coincidences. You had very low rate. Well, very low. I think it's still quite a few if we consider that we have 4 detectors, if we will have like 8, then it would be much more. But at the balcony, it was like 4 times more almost than in the lab. So the conclusion is that measurements conditions have very significant impact on the results, which is not surprising, but it's nice to see it on your own eye, by your own eye. So then I have a little surprise. I know that Professor Diaz is absent, but I would like you to maybe listen to some measurements to see if you could spot some behavior, some pattern or anything, because there is one little, a very small one. So I will tell you data, counts per hour in time, how it changes in time for one detector, detector number 2, I could say. Now in the second detector, the last record, which is the sum from all of the detectors. Okay, so it was a little experiment and it wasn't perfect, but I did it last night, inspired by the sonification day. So now I can show you the plots. The last audio was this plot, sonified, when you probably can see that for first 24 hours, there was around 7,000 signals per hour. And then there was a little more, about 200 more. But I think even at looking at this plot, you could skip it. Well, obviously in this other scale, you can clearly see it. I don't know what that behavior means, probably nothing significant. It was from this balcony measurement. Maybe it was just atmospheric conditions because it was that weekend that temperature dropped and the snow fell for the like 2 weeks ago, I think. So maybe it was snow, maybe it was atmospheric conditions, I don't know. But to know what we have really measured, we need to have some analysis, which consists of simulations of detector's response to different particles, different cosmic rays, simulations from Corsica of air showers and the density of cosmic ray particles on Earth, and then you can add this up and compares your estimations with measurements. So about the simulations of detector, I would like to talk today because those other parts are not ready to present yet. So we want to estimate how sensitive our detectors are to different particles, which mean when a particle of certain momentum hits our detector, we need to have an answer if it will produce a signal that is high enough so that we can actually register it. To do so, we use 3 and 4 software, which enables full control over the geometry of experiment, parameters of used materials, and it does all the physics for us, so we don't have to worry about many things. And we consider only muons, electrons, and positrons together as equal and photons. Because, well, in cosmic rays, you have mostly those particles, and neutrons can be detected by scintillators. Okay, so here you have a picture of our detector in the simulator. You have a scintillator covered by an aluminum foil, which reflects photons and keep them inside scintillator. Then you have a layer of black tape. And above that, you have a layer of some steel plate or other shielding. We chose steel plate because it was steel plate that we use to cover the box for outside measurements. And and I will explain in a moment why steel plate is a good choice. Here are some parameters of our detector composition, but it's some technical details. Here are some photos of visualization of these simulations. So this is an example of electron at the momenta of 0.01 GeV at theta angle equal 30 degrees. So you can see it passes through iron, it hits the scintillator, and the green lines are photons. So the scintillator is filled with photons, and we have a lot of photons here at the CPM that is right there. This is an example of a gamma ray hit. So you can see that there was some electron produced in the scintillator, and then you have a muon at 1 GeV. And this is a photon detection efficiency. This is a very important function that we put in the simulations, and it is a probability that even if a photon hits our photosensor, that it is detected, because photon can hit our CPM, but our CPM is sensitive, have different sensitivity to photons of different wavelengths. Okay, so how can we calculate the amplitude of signals that were produced? Well, it is everything. Everything is actually described in the documentation of CPM. From simulations, you have number of photons that were registered by the CPM after filtering it with this photon detection efficiency. And you can calculate the amplitude of produced signals with this formula. We have also some parameters like percent of how much of a surface of CPM is covered by microcells that produce the voltage. You have number of microcells on this CPM, and you can calculate from the parameters of the CPM you use this voltage per microcell produced. And the sensitivity of our detector, if we have, for example, 100 events, and from 100 events, 70 produced signal that's amplitude was higher than some value, then we have 70% sensitivity to the particle with that moment. But sensitivity is not uniform among the surface of the detector, and it can also depend on the angle at which particle hits the detector. So we chose to study the effective sensitivity, which is, well, like an average sensitivity over the whole surface. And here is, so we created some maps of the detector. We have mapped the detector by shooting particles to different regions of its surface. And this is how it looks like for an electron of that momenta. And it was perpendicular case. This is a case when where particles go from this side, so we can see that they can also hit the sides of our detector, not only its top surface. And here we have photons coming from this direction on the diagonal of our detector. So what are the results actually? Here are the results for photons. We chose to represent it as a function of particle momenta. So this is where our Corsica simulation cut the particles. So we don't have particles below that threshold. So unfortunately for photons, there is some sensitivity here. So we cannot predict those particles in our simulations, but some of them will be detected by our detectors. And you can see that when the momenta increases, the sensitivity also increases, and it also increases with the inclination angle. It is probably because photons passes through thicker layer of steel plate, and there is more probability of some pair production or something like that, because those events also occur. And this was for photons. This is for electrons. You can see that, well, here the efficiency is very low. the sensitivity around 10%. And for electrons, you can see that it grows and it reaches its maximum value of 100% at some value. This value depends on the inclination angle, which is not very convenient, but we have to deal with it. And you can see that below this threshold for Corsica simulation, there is probably actually no sensitivity at all. So it's good. It means that our steel plate has stopped all the electrons that we didn't simulate in the Corsica. So we have a better picture for electrons here. And for muons, well, they reach also this 100% sensitivity at some value of momenta, and they reach it actually very fast. It also depends on the inclination angle, but not as strongly as in case of electrons. We also checked how it looks for different shieldings. And you can see here some examples when there's no shielding, there's some aluminum, some iron, some steel, and some glass. And you can see that, well, for photons, actually, the thicker the layer of shielding, the better the sensitivity for higher momentum. So probably there's some processes that produce electrons, which actually hit the scintillator and produce signals. For the electrons, you can see that thicker layer, well, shifts this sensitivity reaches its maximum to the higher momenta. Without any shielding, our detector is almost 100% sensitive to electrons of even low energies like few MeV. So here you can see how significant, even when you go from 1 millimeter of steel to 2 millimeters of steel, you can have very different results. So let me finish. So from the measurements, you can clearly see that conditions have huge impact on the results. Frequency of our signals is relatively high, so I think measuring some oscillations and some periodicity in the cosmic ray flags is possible. And they work, and they didn't broke outdoors measurements. And from simulation, you can have similar conclusions. So shielding and what you put above the detector has huge impact. And you can see that, well, sensitivity for photons is low, but I think it's not negligible. It's around 10%, and it can be higher for higher moment. So in the future, well, in the near future, we plan to construct a second array that will have all of these upgrades. Probably I need to add some audio element to produce sound when there is a signal. I would like to perform a long-term outdoors measurements that would last like a month, and it would be on the real plain sky, just a steel plate, and the plain sky above our detectors. We need to optimize software. We need to work on the data format and remote data acquisition. And I would like to prepare full documentation of the project that will be published on our Redmine. And I would probably send the part about simulation of scintillator detector really soon, because it's almost finished. And so actually anyone who would like to can read it and build such array for yourself. And thank you for your attention.
Okay, questions or comments? Thank you. You had this interesting finding that your coincidence rate on the balcony was higher than when it was outside. Could you explain that?
You mean it was inside
the building? The rate was higher than outside.
I assume that something happens in the in the walls and in the floors that probably produce more particles. But for now, the statistics are low. I would like to have long-term measurements and see how it looks like in many different conditions.
So I'd like to share our experience. We have found a similar thing in the past, and we were very astonished. It was a bit strange. And we have found very strange things, like we had put detectors relatively high coincidence at a building, and it drastically dropped. So we started to investigate that in detail, and we had a paper on that. And for my talk, I will include the UI so you can get the reference.
Thank you.
What the finding was, the conclusion was very interesting one, that mostly these things come from air showers which are initiated by muons. Decay somewhere a kilometer to above creates an electromagnetic shower, which is relatively compact, on the order of like a few hundred meters, or that's the air's radiation length, okay? And that's what creates many, many secondary particles. If you have a building roof, or we have put lead layers above a pair of detectors, can generate a lot of electrons from gammas, which are inside this air shower, okay? And that's what creates you a lot of particles. And people, I think, that have found that, so that first, if you put the detector outside, you get a certain number of particles, then you increase the thickness above that, you get more and more, and at some point you lose all the soft particles, people call it soft particles, and then you get the constant muon. So it's an interesting thing, and one have to be very careful if you would measure a coincidence rate. So if you put an array of detectors inside the room, you get a coincidence rate. It's not air showers.
It's a shower, electromagnetic shower from the building.
It's an electromagnetic shower which is enhanced by the building structure. One more question. You were showing the efficiency for gammas. Did you include coincidence in that? So did you request two scintillators?
No. It was.
Then you should drastically reduce that efficiency, right?
It is for a single detector underneath a layer of shielding.
Okay.
Please, Marcin.
I have the comments about these balcony effects. I used the cosmic watch detectors many times with students. And what have the balcony? Balcony have this small concrete wall. It's a source of secondary particles. I suppose that you put on the balcony, and near you have this small wall.
Yeah, it was like this wall was from one side, and
that's why my experience was that when we measure with students by using the cosmic watch inside the building and outside, decreasing of signal was on the level about 10%. We saw these effects, but the ideal for me method for this is forget about photon and electrons in detectors like this. To create the systems considered as two detectors. And in this way, you will be measure mainly muons.
So if I will have like 8 detectors in an array, I can have like 4 double bottom coincidence.
It will be better because muons coming mainly from the cosmic shower, not from the secondary cascade from the buildings. And of course, if you measure outside, minimum length from the building should be few meters, minimum length, because of influence of building. Something like that. But why are you simulate the shielding, aluminum shielding, steel shielding?
Because currently the steel shielding is because I want to put them outside. So I have to, some sealed it up from from snow.
A box.
Yeah, it was just a box.
Okay, because from the literature, when you want to use the shieldings, we're talking about lead shieldings, and you need minimum 5-10 centimeters of these lead shieldings, and maximum. It means that literature told us that maximum thickness of the shielding is 13 centimeters. After this thickness, nothing changing. It means that after that you measure only muons. Because muons are not sensitive for the buildings, but of course they are sensitive, but not so much.
You like 30 centimeters of lead, it's costly.
Yes.
And it weighs a lot, so I don't trust my roof that much.
But what can I tell? I had measure with lead shieldings, and if we put the shieldings less than, for example, 1-2 millimeters, we increasing the value of counting. Because of this shielding, create a many additional
this electromagnetic shower.
That's why I'm talking that minimum thickness is about 5 centimeters, because 5 centimeters lead give us similar signals like without shielding. This is from my experience, and of course the muons and other particles can create the X-rays and gammas, but you can consume some of them by using the very thin foil of copper and aluminum to consume the X-ray photons, which will be created in your shield.
Okay, okay, thank you.
Let's move this discussion to the end because just I would like to ask if there are more questions or online especially. Well, if not, let's thank the speaker again.
Thank
Jerzy.
you.